Hello everyone, today I'm going to present my project, building a hardware accelerated MIDI synthesizer for my CPU, and my name is Haoren Chen. This project focuses on enhancing a RISC-V processor with custom DSP instructions to efficiently handle real-time audio synthesis. Here is the outline of my talk. I will start with a project overview, then I will present the baseline analysis and explain the main bottleneck. Next, I will introduce the audio design and how I extended the variator test bench. After that, I will describe DSP instructions, multiplier and divider, and updating the firmware to actually use these hardware features. Then I will present the hardware synthesizer block, its memory map, and the signal processing pipeline. Finally, I will explain the system verification strategy and testing coverage. Here shows my goal and what I changed in the system. Make the software synthesizer run faster, move the heavy mass into hardware, and make the simulator able to play sound so debugging is easier. In the system diagram, I added two new devices. One is an audio output buffer and the other is a hardware synthesizer. So I can either the CPU makes audio sample and send them out, or the CPU just configure the hardware synthesizer and the hardware generates sample faster. PicoSynth is a small MIDI synthesizer made for embedding system. It does not use floating point. Instead, it mainly uses Q15 fixed point mask. This works well on small CPUs, but it also means speed depends on how fast we can do fixed point. In terms of structure, PicoSynth is built as a simple processing chain of each voice. Each voice has an oscillator to generate a waveform and envelope to control volume over time. The filters such as low pass or high pass or a state variable filter. Then the voice signal are mixed together. After mixing, the signal go through a DC blocker and a soft clipper. And then we get the final output sample. This design is clear and modular, but it also means that for every single audio sample, we repeat many small DSP operations and we repeat them again for every voice. That is why hardware accelerate is very useful here. This slide shows where the time goes in the baseline run, and it explains why we need acceleration. The initialization steps are small, only tens or a few hundred cycles. The real cost starts when we generate audio. Processing just one sample takes about 85,000 cycles, and most of that time is inside the main loop, PicoSynth process. This is why we focus on DSP acceleration, because PicoSynth process contains lots of multiplies, saturating, and filter. If we speed up this part, we speed up the whole synthesizer. And this slide shows the fixed point bottleneck and what hardware operation we need. Because PicoSynth uses Q15 mask, the most common operation is Q15, so that is the first and most important target. Then inside the main function, especially in filters and mixing, we also need saturating add and subtract to avoid overflow and audio distortion. Some parts, like frequency and coefficient calculation, also need divide remainder. This is why I implemented this DSP operation in the CPU. On this slide, I introduced the audio peripheral design. The audio device is memory map and has three simple registers. First, there is an ID register that returns the word Audi, so software can quickly confirm the device exists. Second, there is a status register that tells me whether the FIFO is full or empty. Third, where is the there is a data register where the CPU writes one PCM sample each time. The architecture is also simple. The CPU keeps writing sample into a FIFO buffer, so the CPU does not need perfect timing. The FIFO then outputs sample at a fixed sample rate, and the varilator test bench capture those samples on the host side. From there, I can either play the sound in real time using SDL or save the sample into a waveform file to listen and debug later. On this slide, I explain how I extend the varilator test bench to verify audio. First, I check that the audio device is detected by reading its ID. Then I confirm the CPU is really sending audio by printing values and marking and making change over time. After that, I dump samples into waveform file and listen to it to confirm the waveform looks and sound reasonable. I also added real-time playback using SDO so I can hear the sound immediately while the simulator is running, so I can verify audio in two ways: by listening to a waveform file or by real-time playback. And here is a 440 Hz sound, and it can let me know the sample right at the right place. On this slide, I explain the DSP instructions. First, I modify the ALU and added a small set of fast operation designed for fixed point audio mask. The biggest target is Q15 because PicoSense use Q15 everywhere, so if I can make Q15 faster, the whole synthesizer become faster. I also added a Q15 multiplier with rounding. The main reason is audio quality. Rounding reduces small errors when we do many repeat calculation. Then I added saturating ads and saturating subject. This is important because when we mix signal or update filter state, values can exceed the normal range. If we do normal integer overflow, the signal wraps around the and create very harsh distortion. Saturation prevents that by clamping the result to the value range. I provide 16-bit saturation for direct audio samples and 32-bit saturation for internal accumulators. And finally, I added a saturating left shift, which is useful for simple gain adjustment without causing overflow. To add the custom DSP OP code cleanly, I modify three main files. First, the instruction. I define the custom 0 OP code and the function code for each DSP instruction. Second, in instruction decode, I updated the decode logic so the CPU can recognize these custom instructions. Third, in ALU control, I added the control mapping that selects the corresponding ALU operation based on the DSP function file. So the key point is this edit connect the DSP instruction encoding, decoding, and the ALU execution together, making the new DSP operation behave like standard ALU instructions in the pipeline. On this slide, I explain why I added a hardware multiplier and the divider. At first, the CPU did not have hardware support for multiply or divide. So it had to use slow software to calculate, which caused many extra cycles. In audio synthesis, we do a lot of math every sample, so this overhead becomes a big performance problem. Sometimes they also need division for parameter calculation, so without hardware multiply and divide, this part become much slower than they should be. On this slide, I show the unit test I used to verify the new hardware features. On the left, I used a DSP test suite to validate that the fixed point and saturation operation behave correctly. It covers Q15 multiplication and with rounding, saturating shift, and both 16-bit and 32-bit saturating add and subtract. On the right, I used a multiplier test suite to validate multiplication result, including normal multiplication and the high power behavior used by M extension style instructions, and these are all passed. On this slide, I show the firmware side optimization where I replace slow software mess with my hardware DSP operation, focusing on the hottest path. The main target is the synthesis loop, because the per sample processing dominant the cycle count, so I apply Q15 multiplication widely inside the synthesis process. Then I used saturating add and subtract for mixing, clipping, and filter so values stay in range without overflow artifact. Finally, I replaced expensive software divide and else in frequency and coefficient calculation. On this slide, I introduced the hardware synthesizer. It supports 4 voices and 5 waveforms. It also includes an envelope, a step variable filter with resonance, envelope control for filter cutoff, and a DC blocker to remove DC offset. From the software side, it is a simple memory map device. The CPU can enable it choose active voices and read the mixed output sample, while each voice has its own setting like frequency, waveform, envelope, and filter. The key point is that the CPU mainly configures notes, and the hardware generates audio more efficiently than pure software. On this slide, I summarize the signal processing pipeline inside the hardware synthesizer. For each of the 4 voices, the signal starts from an oscillator that uses a phase accumulator and a waveform lookup. Then it goes through a step variable filter, which is mainly a small set of repeated multiply accumulate operation to shape the tone. After filtering, the envelope controls the amplitude over time, including exponential style decay for a more natural sound. After that, all voices are combined in a voice mixer using saturating addition, so the mix does not overflow and wrap it around. Then the mixed signal passed a DC blocker with a coefficient around 0.995 to remove DC offset and stabilize the waveform baseline. Finally, the system output one audio sample at the target sample rate. On this slide, I show the test for the hardware synthesizer. On the left, the Scala test suite checks the main features: all waveforms, all enveloped, filter mode, and the DC blocker, envelope to filter modulation, and multi-voice mixing. On the right, Minimal C test configures the device through MMIO and reads back samples to confirm it produces valid audio data. The takeaway is that hardware since passed both unit level test and firmware level integration test. Here is the full system verification result. From the log on the left, you can see the note number 60, which is middle C, is triggered successfully. After that, the system started outputting audio samples. The sample values goes up and down instead of staying constant, which indicates that a waveform is being generated in this test. It matches the expected behavior of a saw wave, so the basic synthesis path is working in simulation. On the top right, the output confirms that the simulator correctly detects the audio MMIO device and that real-time playback through SDL is enabled. However, this part is not perfectly stable in my environment because I run the simulation inside WSL. Sometimes after running for a long time, the audio device becomes unavailable and the SDL playback fails. On the bottom right, I also confirms that the system can successfully generate an output file. When I open a generative waveform file, it contains sound and which proves that the audio samples are actually writing out correctly. But the current audio quality is still not good. What I hear is very low frequency noise instead of the expected clean tone. My current hypothesis is that there is still an issue in the hardware side computation or scaling. So the next step is further debug. Thank you for listening.